Cellulase. Cellulases are an important enzyme for many different organisms. They allow the cellulose in plant cell walls to be broken down and digested into energy. The most common producer of these enzymes are bacteria and fungi, with different bacteria often acting as symbiotes for larger organisms such as termites or cows, where the bacteria breaks down cellulose into more readily digestible forms of molecules. Cellulase is often a complex protein, meaning it has several subunits working together. Cellulase in fungi is typically less complex, having one subunit for catalysis and one subunit for attaching the cellulose, though that subunit may or may not be present. Bacteria, comparatively, can have much more complicated arrangement. Cellulases are divided into 5 different reaction types based on how they digest the cellulose, and bacteria often have a complex containing enzymes for all 5 of these. The 2 most common reactions are done by endocellulases and exocellulases. Endocellulases first break the overall non-covalent interactions that hold together the wall structure, creating single-width chains. Exocellulases then use hydrolysis to cleave the ends of these new chains to create simpler sugars, such as cellobiose and 2-part cellulose sugar. These can be digested by appropriate enzymes to create glucose, which is then utilized by the organism. This same enzyme is also used to process plant material in the formation of biofuels, creating alcohols from the sugars produced.
This is a cellulose cross-linked molecule. What an endocellulase does is come in and break the hydrogen bonds that cross-link the crystal. After the endocellulase comes in and cleaves the hydrogen bonds, forming one single strand of cellulose, exocellulases come in and break the glycosidic linkages between 2 glucose structures. After an exocellulase breaks the cellulose into smaller structures, a molecule such as cellobiase comes in and breaks it down into glucose molecules that can be metabolized by organisms.
This is an example of a cellulase from a bacteria. As you can see, it has many alpha helices, some beta-pleated sheets, and glutamic acids are serving as the active site. Cellulose is bound into the active site by hydrogen bonding from glutamic acid 134 and glutamic acid 231. When the enzyme becomes active, this electron from glutamic acid 134 attacks carbon 1 of the left side of the molecule. This breaks the glycosidic linkage, freeing electrons to attack this hydroxide group, which then breaks the bond between the 2 molecules, allowing this portion of the cellulose to leave the active site. A water molecule then enters and is attacked by the electrons from glutamic acid 231. This creates a negative hydroxide group, which then attacks carbon 1 of the left side cellulose. This then frees the left side to be released, and in the meantime restores cellulase to its original form, allowing it to continue enzymatic activity.
In summary, cellulase catalyzes an important reaction that breaks down cellulose into usable energy for many organisms. Cellulase has many different levels in its reaction, from huge polysaccharides to single glucose molecules, all from one enzyme with many domains. Its many uses include making fuels, and it is very important to the textile and food industries. This is good for everything that we're doing, and these molecules are very cool. I wish that we could continue doing this project for forever because it's awesome, and I guarantee you that I'm having a lot of fun presenting this to everybody. It is great, and the molecules are glucose and cellulose and cellulase in the enzyme active site, because it's great stuff that's going on in this reaction mechanism, and that has to be 2 minutes. And yeah? No? Still talk? Still, oh, it hasn't been 2 minutes. It has not. I think so. I don't know. If it hasn't been 2 minutes, then I don't know what we're still doing.